Good morning, students. Our today's topic is mean value property for heat equation. In order to discuss this property, first of all, we discuss some definitions that will be used. So our first definition is parabolic cylinder. Parabolic cylinder is the set denoted by U with suffix T in the base. This is the Cartesian product of the set U with the semi-open interval 0 to t. T is included. This U is the open subset of n-dimensional real Euclidean space, and this t is positive and is fixed. So this is called parabolic cylinder. Now next to define parabolic boundary of this cylinder. Parabolic boundary of this parabolic cylinder, that is denoted by gamma with suffix t in the base, and this is ut closer minus ut. This is called parabolic boundary of parabolic cylinder. Next, there is an important definition, heat ball. To define heat ball, let us take X is a fixed point belonging to n-dimensional real Euclidean space, and T is a real number, R is a positive number. We define the heat ball as E, which is the function of X, T and R. This is the set of all those ordered pairs Y, S belonging to n plus 1 dimensional real Euclidean space, such that S is less than or equal to T, and the value of fundamental solution of heat equation at x minus y, t minus s. This is greater than or equal to 1 upon r raised to the power n. This is called heat ball. Now let us start mean value property for heat equations. So the statement of the property is U is a function which is twice continuously differentiable function defined on the parabolic cylinder ut. Let us take this U is the solution of the heat equation. Then we are to prove that the value of U at xt, that is given by 1 upon 4 r raised to the power n into the double integral over the heat ball of the function U at ys into x minus y mod square upon t minus s whole square. Here this is true for every heat ball which is contained in the parabolic cylinder ut. This is called mean value property for heat equation. To prove this property, first of all, let us shift the space and time coordinate so that x and t both are 0, and corresponding to x is equal to 0 and t is equal to 0, the heat ball that is denoted by E at r, because this is the function of r only now. And let us define a function phi which is 1 upon r is to the power n into the double integral of u at ys into y mod square upon s square dy ds. Now we are to prove that this function phi, that is equal to 4 times the value of u at origin. To prove this, let us put y is equal to r into y dash and s is equal to r square into at s dash. Actually, we are to differentiate this function with respect to r, and we cannot directly differentiate it with respect to r. So firstly, we will have to change it into unit ball, as we already discussed in the mean value property for Laplace equation. We cannot directly have differentiation with respect to the radius of the ball. So in order to differentiate with respect to radius of a ball, we will have to convert it into a unit ball. Then we differentiate it. So here also we will use the same concept. So first of all, let us convert the ball ER into the unit ball E corresponding to 1. So we have used these substitutions. Y is equal to R into Y dash and S is equal to R square into S dash. Now let us differentiate these two. So differentiating, we get on the left side we get the derivative dy. On the right side we have r raised to the power n into dy dash. Because here y is n dimensional vector, so when we differentiate here we will get r raised to the power n, and differentiating s we get ds is equal to r square into ds dash. And also let us find y mod square upon s square. Putting the values of y and s here and simplifying, we get 1 upon r square into y dash mod square upon s dash square. And also dy into ds, that is given by multiplying these two, that will become r raised to the power n plus 2 into dy dash into ds dash. Now let us substitute all these values in the function phi which we have defined, so that will be converted into the integral over the unit ball. So the value of function phi, that becomes double integral over the unit ball of the function u, which is the function of ry dash r square s dash into y dash mod square upon s dash square dy dash ds dash. Now we have converted the ball into unit ball. So now we can differentiate both sides with respect to r. So differentiating with respect to r, on the left hand side we get phi dash r. On the right hand side, differentiating with respect to r, only u is the function of r here, and so that will become the partial derivative of function u with respect to r into y dash mod square upon s dash square. It's double integral over the unit ball. Now in order to find phi dash r, we require partial derivative of function u with respect to r. So let us find it separately. So let us consider partial derivative of function u with respect to r. Here inside u is a function of ry dash and r square s dash, and according to the notations which we have taken, ry dash, that is y, and r square s dash, that is s, and y is n dimensional vector. Suppose its components are y1, y2, y3 up to yn. So we can say that u is the function of y1, y2, y3 and so on up to yn and s. So by chain rule of differentiation, its partial derivative with respect to r, that is given by curl u by curl y1 into curl y1 by curl r plus curl u by curl y2 into curl y2 by curl r and so on, curl u by curl yn into curl yn by curl r, and last curl u by curl s into curl s by curl r. Now by our substitutions, we have taken y is equal to r into y dash. Y is n dimensional vector having the components y1, y2, y3 up to yn, and y dash, that is y1 dash, y2 dash, y3 dash, yn dash, these are its components. So if two vectors are equal, their corresponding components will be same. So in general, from here we can say that y1 is equal to r into y1 dash, y2 is equal to r into y2 dash, and so on, yn is equal to r into yn dash. So in general we can say yi is equal to r into yi dash. Now if we differentiate both sides with respect to r, so from here partial derivative with respect to r, that will become curl yi by curl r, and here we get yi dash. And now let us differentiate s partially with respect to r. So from here the partial derivative of s with respect to r, the derivative of r square, that will be 2r. So we get 2r into s dash, and therefore we can substitute the values of these partial derivatives to find curl u by curl r. So curl u by curl r, that becomes curl u by curl y1 into y1 dash plus curl u by curl y2 into y2 dash and so on, curl u by curl yn into yn dash plus curl u by curl s into the value of curl s by curl r, that is 2r s dash. Now we can write this expression in the form of summation. So this can be written as summation curl u by curl yi into yi dash. Here I varies from 1 to n, and this term we have taken as it is. And according to the notations of derivatives, this can be written as u with in the base we have the suffix yi, and these terms as it is. So we have obtained the value of partial derivative of the function u with respect to r. Now we can substitute this value in phi dash r. Substituting the value there, this is the value of curl u by curl r, and the remaining terms we have kept as it is. Now let us again convert this unit ball into the ball corresponding to the radius r by substituting the values of yi dash, s dash, y dash, dy dash into ds dash. So let us put the values. Yi dash, that is yi upon r. The value of s dash, is s upon r square. The value of dy dash into ds dash, that is dy ds upon r is to the power n plus 2. And here also you can put the values of y dash and s dash. So correspondingly, this unit ball that will be converted into the ball corresponding to r. Now let us write this expression by taking the term 1 upon r is to the power n plus 1 outside of this double integral, and inside we have summation curl u by curl yi into y mod square upon s square plus 2 times curl u by curl s into y mod square upon s. Now let us take the integral of this function that is denoted by a with this term, and 1 upon r is to the power n plus 1 into the double integral of this term that we have denoted by b. So finally we can see that phi dash r is equal to a plus b. Now the remaining part of this mean value property we will discuss tomorrow.